Now let's see the unboundedness of hyperbola. That is, if hyperbola is a closed shaped curve or an open shaped curve. So for example, the circle is a closed shaped curve, an ellipse is a closed shaped curve, but parabola is not a closed shape, but it's an open curve. Similarly, let's identify the openness or closeness of hyperbola. Now, as we have seen here, the hyperbola which exists in this manner makes us understand that as I proceed on further and further, it opens up and goes till infinity. And similarly on the left, as I see here, this goes on and on and on till infinity as I proceed towards this minus infinity out here. So this makes me understand that this is completely open, but it can never close. This end can never close with this end, and this end can never close with this end. Mathematically, which proves that if I have the equation x squared by a squared minus y squared by b squared equal to 1 as the equation of hyperbola, that implies x tends to plus or x tends to infinity when y tends to infinity and x tends to minus infinity when y tends to minus infinity. Therefore, the curve is unbounded, which clearly shows that when x tends to infinity, y doesn't tend to a finite value but infinity, and when x tends to minus infinity, y also tends to minus infinity. That is, x tends to plus or infinity when y tends to this implies the hyperbola is unbounded. That is, it is not a closed curve but an open curve. That is, open curve is how we understand the relation between openness and closeness. A hyperbola is an open curve and unbounded. Let's see what is the role of horizontal line to the hyperbola. As we see here, I clearly see that for this hyperbola, if I draw a horizontal line parallel to x-axis, then that cuts the hyperbola at 2 points, this and this. That is P and P dash are the 2 points where this horizontal line cuts the hyperbola. So every horizontal line is set to intersect the hyperbola in 2 points. So for example, I take a line in this form. Then this also is set to cut the hyperbola in 2 points, Q and Q dash, and then we get this parallel to this 2 points of intersection. So the learning outcome here is that every horizontal line parallel to x-axis cuts the hyperbola in 2 points is how we identify the property of horizontal line connected to the hyperbola. Now let's see the symmetricity of hyperbola connected with x-axis initially. So for example, I have the standard equation of hyperbola as x squared by a squared minus y squared by b squared equals 1 implies my y is given by plus or minus b by a root of x squared minus a squared from this. Therefore, this makes us understand that for every real x corresponds to two y values, one given by plus and the other given by this, and these two are opposite in signs, is how we understand the corresponding values. Therefore, for every x, one y lies exactly on the above and exactly on the below if I take it along y-axis. That is, if I take the hyperbola in this form, then I clearly understand that for every x there are two values, one on the positive side and one on the negative side. Therefore, the graph is symmetric about x-axis. That is, the symmetricity above and the symmetricity below are exactly symmetric with respect to x-axis. That's how we understand the symmetricity of the hyperbola with respect to x-axis. That implies the hyperbola is symmetric about x-axis, as can be seen here. High symmetricity of hyperbola with respect to x-axis. This acts as the mirror in reflecting the surfaces of each other. Now next is identifying the symmetricity about y-axis. So in a similar manner, I take the equation of hyperbola in standard form with this implying that my x is plus or minus a by b root of y squared plus b squared. Therefore, if I have my y, which is a real value of y, corresponds to two values of x, one given by a by b root of y squared plus b squared and the other given by minus a by b, this. That means every x has two corresponding values, which makes us indicate that I get the symmetricity about y-axis. That means they just change in opposite sign, and therefore this part of is said to be symmetric about this side. So this is how I get the symmetricity about y-axis. All the image on this right is exactly same as this, or this distance will be same as this distance, or any point you take will be exactly the reflection of that point along y-axis. That implies the hyperbola is symmetric about y-axis, is how we conclude. Therefore, finally we conclude that an hyperbola is both symmetric along x-axis and also along y-axis. Similarly, we have the ellipse, which is symmetric along x-axis and symmetric along even y-axis. A circle is symmetric about x-axis and symmetric about y-axis, and hyperbola is symmetric about x-axis, but the symmetricity about y-axis does not arise because the graph does not cross y-axis. Is how we understand the concept. Now let's see the connection of the distance from focus to any point in the hyperbola, which is related with a, that is half the length of major axis. So as we know that the standard equation of hyperbola has its shape in xy coordinate system in this form. Now this hyperbola given by equation x square by a square minus y square by b square equal to 1 with a greater than b has the focus connected with a. That is, if I take any point P on the hyperbola, and if I have the focus S, which is out here, then I'll connect S with that point P on the hyperbola, and I connect the other focus connecting with this. So I have SP, the distance from focus to the point, and S dash P, the distance from other focus to the same point P, x1, y1. Then mathematically I have the relation between SP, S dash P and A, which is the distance from center to the vertex. This is A. So this distance is connected with the distance as S dash P minus SP equal to 2A. That's how we connect the relation between SP, S dash P and A. So S dash P minus SP is equal to 2A, which is a constant. And this is referred as the distance AA dash. So the distance AA dash is 2A, which is connected. So SP plus S dash P is equal to AA dash, which is 2A, or S dash P minus SP is AA dash, which is 2A. Now let's see the general notations for hyperbola. In general, the standard form of hyperbola is denoted by S identically equal to x squared by a squared minus y squared by b squared minus 1 equal to 0 is how we denote the standard equation of hyperbola. Now in this, if I take the point P x1 y1, then its corresponding S1 is defined as x1 by a squared minus y1 by b squared minus 1 equals 0 is what we get for x1 y1. If suppose I have then its corresponding S11 is denoted by x1 squared by a squared minus y1 squared by b squared minus 1 equal to, it's not equal to 0. This is a constant value. So this is a constant value. So this we don't equate to 0. So S11 is a constant value. This is an equation. This is a constant value. And this is the equation of hyperbola. And suppose I want to find S12 corresponding to 2 points x1, y1 and x2, y2. Then equation of S12 is given by x1, x2 by a square minus y1, y2 by b square minus 1 is how we define the different types of notations which we have, which is hyperbola, which is a linear straight line, which is a constant value and a constant value. Notations for hyperbola are denoted with S, S1, S11, S12, S22, etc. Transverse and conjugate axes. What are these two axes for the hyperbola? Let's see through the ellipse in standard form. Say I have the equation of ellipse in standard form with y-axis and x-axis. This is A and A dash and B and B dash. Then the distance between A dash is 2A and the distance between B and B dash is 2B, and usually the line which consists of A dash is called the transverse axis, because this axis passes through A dash, and the line which passes through B and B dash is called the conjugate axis. So in case of standard equation of hyperbola, this is transverse axis and this is conjugate axis. For the hyperbola, x squared by a square minus y squared by b squared equal to 1. So the transverse axis equation is given by y equal to 0 and conjugate axis equation is given by x equal to 0. That is, the x-axis is the transverse axis and y-axis is the conjugate axis. Now next is about length of transverse and conjugate axis. So now that we have discussed about transverse axis being the x-axis, or which passes through A and A dash, and conjugate axis is about y-axis which passes through B and B dash. So here the length of transverse axis is given by A dash, which is equal to 2A units. Out here, and the length of conjugate axis is BB dash, which is 2B, and therefore the length of conjugate axis, that is BB dash, is 2B units. Is how we get this in hyperbola. Transverse axis and conjugate axis have their lengths 2A and 2B respectively. Now let's define the chord of the hyperbola. So as we have the standard hyperbola, out here we see that a chord is a line which joins 2 points of the hyperbola. Suppose I take a point P dash out here and I take a point P out here, so that So this is one of the chord PP dash. Or if I take this with this, I have Q with Q dash, which are chords. So the different types of chords, there are infinitely many chords which we get. So this being a chord and this also being a chord. So because there are infinitely many points on the hyperbola, there are infinitely many points which act as the chords as pair of points. Therefore, we conclude saying that there exists infinitely many chords for the hyperbola. Is how we identify this property. Now let's take a special case where a chord through center of hyperbola has a very specific geometric property. That is, if I take an hyperbola in standard form, with x-axis and y-axis, then if I take a chord passing through the center of ellipse or the hyperbola, then geometrically, if this is the point of intersection of this line, then it makes with center of ellipse this and this will be equal. That is, C bisects PP dash. That is, CP will be equal to CP dash. That is, C bisects P dash. So any chord which passes through the center, then the center bisects that chord is what we identify as the hyperbolic property. Similarly, if I have this with Q and Q dash, then this will be equal to this as the bisector. And then similarly, if I have R and R dash, then CR will also be equal to CR dash. Therefore, I conclude saying that center of hyperbola bisects every chord that passes through it. Is how I identify the property, geometrical property connecting the center of hyperbola with the chord. Center of hyperbola bisects every chord that passes through it. Any chord I take which passes through the center bisects. This equals this equals this, and this equals this. Is how we understand the geometric property with center of hyperbola connected with the chord.